last class was somewhat, there was too many things done with just one slide. So I'm just going to go through some of what we have done last time, but somewhat more structured form, and then go from non-deterministic case to POM-DP, the decision theoretic case, POM-DP case, mention and introduce the model, and start talking about what would be involved in finding the optimal policy. And then we will talk about the algorithmic self-actions. Okay. So part of what we started doing last class, which, basically this stuff is a quick repetition of several of the things we said last time. Okay, so I was trying to draw this last class about the three axes at least we were looking at, and I drew it again after I went back. So you have your action, determinism, stochastic and non-deterministic axis here. You have the goals, full versus partial satisfaction axis there, and then the thing that we added essentially is the satisfaction, the observability issue, and you have fully observable, partially observable, and unobservable. For the partially observable, by the way, I used the word categorical last time. That doesn't make as good a sense. Just use it as perfect sensors versus noisy sensors. A perfect sensor essentially means if it gives an observation, that observation holds in that state. A noisy sensor, if it gives an observation, that only holds with some probability. Okay, so as I mentioned, as we mentioned last time, essentially, if you have, if you think in terms of observations as this model, probability that you get observation O in state S. For perfect sensors, this is either 0 or 1. Okay, either you get the observation or you don't get the observation with 1.0 probability. Whereas for the noisy sensors, it's actually between 0 and 1. Okay, so that's the issue. And then just because you have perfect sensors don't mean you have full observability. You may be able to perfectly sense certain aspects of the state, but not other aspects. So in fact, it is useful, although we'll come back to it later on, it is useful at this point to think in terms of, let's say, states with state variables, let's say P1, etc. to Pn. Okay, so if you have state variables P1, etc. to Pn, then you may well be able to have, what I'm saying is I'm considering going from atomic state description, I'm looking for a minute for state variable descriptions. And so the state variables, let's say, are P1 to Pn. So that essentially means assume these are all Boolean state variables. So there are obviously 2 power n states that these can describe. Okay, so I might, for example, what can my observation actions do? My observation actions might basically be able to sense P3, for example. That could be an observation action. And it will tell you for sure whether P3 is true or false. Okay, so sense P3, if it says, it will say true or false. And if it's a perfect sensor, when it says it's true, it's for sure true. When it says it's false, it's for sure false. If it's an imperfect sensor, when it says it's true with some probability, some arbitrary probability. Okay, now I can, for example, have sensing actions on P3, P4, and P5, let's say, and nothing else. Then I have perfect sensors, but still not fully observable because I know a whole bunch of, there are other bunch of state variables or features of the state that I cannot actually observe. Okay, so that's the point I'm trying to make about full observability versus perfect sensing, perfect sensors. Okay. One other thing, since we're talking about this here, in essence, if I actually only have one sensor, suppose I have P1 to P10, P1 to P10 as my state variables. They're all Boolean. Okay, so then I have 2 power 10 are 1024 states. Right? Okay, so suppose I only have a sensing action on P3 and nothing else. Okay, so all I can do after I do this action essentially is I will be able to tell whether I am in P3 equal to true and everything else, or P3 equal to false and everything else. So any state where P3 equal to true is observationally equivalent as far as we are concerned, because this is the only observation action we have. We'll never be able to distinguish between these states. And then similarly, all these states are observationally equivalent. So you want to think of these are observationally equivalent classes, and you will say that you have full observability if the observationally equivalent classes are singleton states. That means you will be able to tell each state uniquely. Right now, notice that there will be 512 states here and 512 states here. Right? Okay, that's why it's basically, if you only have sense P3, then you have 512 states. If you also throw in, let's say, sense P5, and these are the only sensing actions you have, then eventually you will be able to split it into 4 observational classes, each of 256 elements each. Okay, and I would say I have full sensing, full observability if the observationally equivalent classes are all singleton sized. Okay, so that's the thing that you want to be able to keep in mind. Right now, we'll come back to the observational model in a minute, but essentially we are assuming this is a general enough model to also capture that. Because it's just giving some observation. So in our case, basically it takes a state and gives you the observation about whether P equal to true or P equal to false. P1 equal to true or P1 equal to false. Yes?
So if we have 10 sensing actions that can sense the values of P1 through P10,
yeah,
and that way we can get these singleton
exactly. Yes, it is true.
Observable.
Yeah.
Even if we associate some kind of cost with each of the sensing actions, we want to minimize the cost.
That's also true. And what's more interesting, since we're talking about that, actually, in fact, the problem, if you think in this level, okay, it's sometimes you may not actually have sensing actions that will sense every variable. You heard of words like hidden variables, right, all your life. And it's called hidden variable because it cannot be sensed. Okay, it has to be sensed through other variables, for example. Okay, and in particular, you may not be, your sensing actions, for example, may actually do things like this: sense P1 or P5. So it will sense the truth of a particular logical formula, P1 or P5. It won't tell you P1, whether P1 is true or P5 is true. It will only tell you whether one of them is true. Do you see what I'm saying? So once you have those kinds of sense, that model also can be captured by, I will give you an observation given when you give me a state. Turns out this, at this level, this is a simple enough atomic level observational model that either this kind of sensing actions can be captured there. Okay, but it is useful to think, because this is how we tend to think of states as features, feature vectors. And so sensing actions are trying to tell whether certain features hold in the states. But sometimes the sensing actions may not be able to tell, for every feature, they may not be able to tell whether the feature holds in the state or not. They may be able to tell whether some complex formula over the features holds. Okay? Anyway, so going forward, so this was the dimensions that we were talking about. And the minimal things I want you to remember from this is that these are orthogonal dimensions. Okay? And that classical planning corresponds to that. Okay? And we also mentioned that some people do consider, a minority of people consider classical planning as corresponding to deterministic, full satisfaction, unobservable. They assume somehow initial state is separate. So, and if I tell you initial state uniquely, then I don't need observation after that.
Right.
We mentioned that also last time. Okay? And then form DPs, fully observable MDPs are of course stochastic, fully observable, and general reward function. Okay? And then non-DPs, which basically are non-observable MDPs. Okay, so that would be, they will have stochastic, unobservable, general reward function. So pretty much every arbitrary combination of these dimensions will give rise to a planning problem, a decision-making problem. They are completely orthogonal. Okay, and then one other thing that we mentioned, especially on this and this axis, we mentioned that the difficulty of decision-making, so the success possibility of the agent is lower here, higher here. If you are in a world which is fully observable, you're more likely to be able to succeed and reach your goals. If the world is unobservable, you are less likely to succeed and reach your goals. And similarly, if you are in a world which have deterministic actions, you're more likely to be successful in achieving your goals. If they have non-deterministic actions and you have no clue which of the effect, which of the outcomes are more likely versus less likely, you are have lower level of success. But on the other hand, the reasoning, in fact this comes out today too again, the reasoning that is involved in coming up with the the optimal policy would be higher here in the middle rather than at the ends. So in some sense, finding the optimal policies for partially observable worlds, everything else being constant, would be harder than that for finding unobservable worlds. Okay? And similarly, finding optimal policies for stochastic worlds would be harder than finding those for non-deterministic worlds. And I want you to get that intuition clearly in your head. Okay. And then we went through this whole thing. First, we basically, even though we're talking about observations mostly, I wanted to we talked about non-deterministic actions first. Okay. And the non-deterministic actions, essentially, if you just consider non-deterministic actions, then you essentially, and if you still have full observability, then you have to search in the space of states, except your plan would be a tree. Because you do an action, and then the action will tell you which state you got into, and then when you did get into that state, you can observe it, and then you decide what is the next action to do. Okay? So for non-deterministic actions, you will essentially be looking for contingent plans, that is, plans which essentially say, do an action, observe, based on the outcome of the observation, do another action. What is interesting is that so those are conditional plans. So we will talk a lot about conditional plans. So a conditional plan is of the form, do action A1, and then do the observation. If the observation is O1, do A2. If the observation is O2, do A3. That's a little conditional plan. Now, we will find that conditional plans will be useful to deal with non-deterministic actions when full observability is there, as well as non-deterministic actions when partial observability is there. Finding these plans involves search in the state graph for full observability and search in the space of belief state graph for partial observability. The solution is the same. Solutions will always say, do an action, do an observation, based on that, do another action. Okay, but finding them in the non-deterministic but fully observable case is easier because you're searching in the space of states. In the other case, you're searching in the space of belief states, and there are exponentially more belief states than there are states. Okay? Okay. And then in terms of just state uncertainty, that means if you have full observability and you are doing, you have state uncertainty to begin with, and you're doing actions, actions can be either deterministic or stochastic. We talked about this last class. Okay? And in particular, the size of the belief state can only reduce if you do a deterministic action. So for example, if you have state uncertainty, we use belief state representation. And a belief state is just a set of states. Okay? And the belief state representation, within the belief state representation, you can talk about the cardinality of the belief state, which is how big the state is, how many states are there in the belief state. And again, the idea is that any state which has zero probability is just removed from the set. Okay? And then we talked about the fact that when you apply a deterministic action to a belief state, its size can only reduce. It may remain the same or reduce. Whereas if you apply a non-deterministic action, it can both increase and reduce. Okay? And the other, so this is basically, that's the point that this is making. So you can have, suppose you started with an incomplete initial state and you only have deterministic actions. So the belief state, initial belief state size is greater than 1. Okay? And as you do actions, essentially the later belief states can only reduce in size. Okay? And then if you have complete initial state, that means you start with belief state size to be equal to 1, and then you do non-deterministic actions. Okay? Then essentially the belief state size can increase as well as reduce, depending on how that non-deterministic action works. Because notice that non-deterministic can include deterministic actions as a special case. Okay? And then the more general case is incomplete initial state and non-deterministic actions. In this case, you start with BI greater than 1, and then the size of the belief states increase and reduce as you keep going towards, as you keep applying actions. Okay, we talked about that too. And then in general, if you have, so this case here, we are assuming no observable, no observations. So if you have non-observable world, that means you have no observation actions whatsoever. So you start from a belief state, all you can do is keep doing actions until you reach a belief state where you think the goal is satisfied. The one question that you want to ask yourself is, suppose, G of S is true for, some goal, you have some goal condition G, and G of S is true for some states and false for some other states. And normally when you did plans in single, in the fully observable deterministic action scenarios, you kept going until you reached a state where G of S is true. Now you are actually going to go from belief state 1, blah, 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 up to belief state n, and I need to decide whether I can stop here right now. I realize that this is going to be slightly more taxing thing because I'm not running in front of the slides, but please don't sleep in front of me because I also will feel like sleeping. If you must sleep, and I know who you are, you know who you are, go wash your face and come back, because otherwise I'll feel sleepy because you're sleepy. Okay. So the question is, I have belief state, n, and I'm going to stop there. Okay. What is my termination condition?
We can specify a condition that if the belief state is this small, then we can stop. So that determinism, this much determinism is obtained.
So actually that's a different issue. So for example, in non-deterministic scenarios, there are two kinds of termination constraints. One is strong plans. So that means if you do the plan, you can stop and say, I have reached a state where the goal is satisfied. I myself don't know at the time when I made the plan what state I will reach. Okay? But basically, it may, maybe I would stop, let's say, at BSN. Now that might well be, S1, S5, S7. Now if I'm stopping there saying, I know I will reach either S1 or S5 or S7, but I'm sure that will be a goal state. What do I mean? Yes? All of them. That's what it means. That is exactly what it means. You can only stop if G of S is true. G of S1 is true, G of S5 is true, G of S7 is true. You can only stop, for strong plans, you can only stop if the entire belief state satisfies the goal condition. Every one of the states in the belief state must satisfy the goal condition. Even if one of them doesn't, then it's not a strong plan, then it will just be a weak plan. A weak plan basically is at least one state satisfies. That's about it. The problem with weak plans is you don't know how weak is weak. You know that it's less than 1, but is it like 10 power minus 7 probability or 0.99 probability that you will succeed when you actually do this? Okay, that's the thing about non-deterministic planning. This is what we were mentioning last time too, that in the case of non-deterministic planning, finding weak plans is not a particularly well-motivated problem. Okay, so you must look for strong plans. And there are many problems for which there may not be any strong plans at all. And for all those problems, the agent can say, so suppose I have, let's say, 100 problems, okay? There may only be strong plans for 9 of the 100 problems. Okay, if your world is bad enough, then there are only strong plans for 9 of the 100 problems. That means for the other problems, the best plan will still have some probability that you will fail to reach the goal state. Right? Okay, so then essentially an agent which is looking for strong plans alone essentially can say, I'll say the problem can't be solved. And it will be right with 91 by 100 probability of being right. So agents get to be lazy without actually solving the problem because most problems can't be solved. Do you see what I'm saying? Whereas if on the other hand, what I really like to say is, do your best or get me a plan which will reach the goal with 0.7 or more probability. Then the agents can't just give up right away. Which is why finding strong plans is somewhat of an easier decision problem intuitively than finding problems that will satisfy a certain stochastic bound. Okay? So non-deterministic normally means that you don't have any probability information, and if you don't have probability information, all you can is differentiate between is strong and weak. And strong plans are not, for many realistic worlds, there are no strong plans. Imagine trying to come up with a plan in a real world which is guaranteed to succeed. And if you said, I'm never going to do an action if I don't have a priori guarantee that this plan will succeed, then you don't have to do any actions in any realistic world. Because everything that you aim for there is a small probability that your plan will fail. So you can just say, I don't feel like doing anything because I know everything will fail with some probability. None of them are a strong plan. Okay, so conformant planning essentially searches in the space of belief states. So here, of course, this is one state and this is one state. And then when I apply an action, I have to apply that action to both the states, and then I will get the new state where, so for example, in this particular case, suppose I have S1 and S2, and suppose action A, we did this last time, action A in S1 will give me S11 or S12. And action A in S2 just gives me S3. Then if I apply action A to this, then I will get a belief state S11, S12, S3. Okay, so I can continue applying actions from this until I reach a belief state where every one of the states in the belief state satisfies the goal condition, in which case I get to stop. Notice that I'm thinking not generalized reward metrics, but just goal achievement conditions. So this idea is called conformant planning. And here is, for example, this is actually the picture for the vacuum agent domain from the book, where essentially there are just two rooms, and they may or may not be dirty to begin with, and the vacuum cleaner is in one of the rooms, and all you need to do is take a bunch of actions such that when you're done, both the rooms are clean. It doesn't matter where the vacuum cleaner is. The problem is the vacuum cleaner has no clue which room it is in. It's one of these Roomba vacuum cleaners, and it doesn't have sensing. Right? So can I just give up because I don't know where I am, or is there a way I can still do the planning? And what this is saying is, in the beginning, in the very beginning, you must have been in one of the states that the world will allow. And those are the 8 possible states. And this is actually a nice little diagram, right? So in these 8 possible states, if I do right action, notice that my belief state now will be this. Right? Because irrespective of where I am, if I try to go right, if I'm in the right, then I'll still be in the right. If I'm in the left, I will now be in the right. So after I do the right action, I'll only have the 4 states among these 8 states which have the vacuum cleaner in the right. Okay, one small question here is, you can define actions in general to have feasibility preconditions. That means if a certain condition is not satisfied, the action doesn't have to actually take place. It's undefined. Okay, so for example, I might say I am allowed to go right only if I'm in the left room. Do you see what I'm saying? If I'm allowed to go right only if I'm in the left room. And if I said that, and if in a fully observable world, this is a very reasonable thing to do. If you're in the right room, why are you trying to go right? It doesn't make any sense. So if you're in the right room and you try to go right, then this action says it's not defined. What happens when you try to go right in the right room? And nothing, if you said that, the world doesn't come, your planning problem doesn't collapse. Okay, it's a reasonable thing. In fact, actually having preconditions will be useful because you won't try every action in every state. Because some actions are not even applicable, so you won't try them. The fewer actions you try, the smaller the branching factor in the search space. So it's like a nice thing to have preconditions. Except, this is a technical problem, if in fact I don't know which state I am in, right? That basically means at least there exists one state here where right is not allowed. So after doing right, I have undefined. So then what happens? Then what happens is, essentially, I have a scenario where, let's say, I am in S1 or S2, and action A is defined for S1 and gives me S11 or S12, and action A is not defined for S2. It's not defined.
So it gives.
Okay, so now you cannot apply this action to this belief state. It's undefined.
Yeah.
You can see this as a bug or a feature. If you're still awake.
So,
Right? It's a feature because, if you see it as a feature, then basically you're saying, previously there were a couple of states where this action is not applicable, so the branching factor in those states will reduce. Now, any belief state that contains this state will not have this action anymore. So it's a feature in that case. But it's a bug also in the sense that way you will never be able to actually come up with plans. It's bad enough that we are looking for strong plans. And I already said that for most realistic problems, there are no strong plans. Now, if I'm also saying strong plans using actions that have feasibility preconditions, then I have even lower chance of finding strong plans, because any time I wind up doing an action that is, it's done in a belief state where at least one of the states, the action is not applicable, I get to stop there. It's like a no good, it's like a prune. You can prune that state at that point. Which looks like a good idea because now you'll be done much faster. Okay, so in fact, if 9 of the 100 problems had strong plans, maybe one of those 9 problems have strong plans that will also work with feasibility preconditions. So you can be even more aggressive in saying, can't be solved, can't be solved, can't be solved, and you'll be right most of the time. But we draw the line there and say, no, let's actually have actions which are total functions. That means for every state, they are defined. Okay? And if they're just not supposed to be done in that state, we'll assume that the state remains the same. It just stays in the same place. Do you see what I'm saying? Now, this is interesting because if you remember from 471, those of you who remember from 471, the strips planning operators, they all have preconditions and effects. So you're in essence saying actions cannot have preconditions anymore, because if you have preconditions, then there are states in which actions are not applicable. So from a state-oriented, from a strips planning perspective, in conformant planning scenario, in belief state search, we would like to think of actions as having conditional effect. So for example, if there was some action A which required P and Q to be true before and gives R as a strips action, that we could change this as an action A which requires nothing. That means it's always applicable. And it basically says if P and Q are true, then R is given, else nothing. Which means, and if you remember the strips actions, they do doctoring over the state description. So if there is no effect, that means you remain in the old state. Which basically means that actually you would like conditional effects, actions which have conditional effects, so that you can be left in the state if the action is not applicable. Okay, yes?
So if we take an action like the right action will only be taken if he is in the left room. So who will actually tell him that you are in the left room and this is undefined?
No, that is actually one other way of looking at it. So in essence, in fact, when the action, so the undefined, if you think of undefined as the logic just fails, that's what this is. The logic, basically, logically you have no, the next state is not defined. But undefined in the sense you'll break your back. Like for example, okay, don't lift things that are actually stuck to the table. So try to lift only things that are not stuck to the table. Right? Now, well, what happens if I try to lift things that are stuck to the table? When I actually do it in the real world, I'll just break my back. And that's not undefined state. It is a very well-defined state. I just go to the hospital now. Right? Okay? And in fact, I think again, this is the point I'm trying to make is, if you have preconditions, logically you are saying if the preconditions are not satisfied, you cannot even ask the question, what happens if I do this action in that state? In real world, that's not true. In real world, you get to do every action in every state.
So
and if it just, if basically you fail in my particular case, when I try to lift this, when this is actually stuck to the table, it won't move. There is some other additional effects it gives me, such as, my back state is now gone. Okay, I broke my back. Okay, so from that point of view, too, actually having preconditions for actions is not a realistic assumption. It's useful to cut down actions that you will consider doing from a given state. Okay. So, but it becomes a very big thing here, essentially, because you actually know that most actions cannot be done in most belief states. Because even if there is one bad egg, you can't do the action. Okay, and so the other thing, of course, is when you do stop. So for example, in this picture you realize, that this is the entire state space, by the way. This is the entire state space. This is the entire reachable state space, with the actions going from belief state to belief state. Okay, and then notice that these are the two goal states. These are the two goal states. Right? Actually, in fact, these are also goal states. As far as I'm concerned, these are also goal states. Actually, it turns out in this problem, I can reach a goal state of keep both rooms clean and you always stay in the left room after you're done. That's your place. That's still possible. Because in the last, after you're done with everything, you do a left action. If you're already in the left room, you will still remain in the left room. If you're not in the left room, you will get into the left room. If all you said is, just get both the rooms clean, then you can stop either with this or this state. If you stop with this or this belief state, then you're in trouble. Because that would only be a weak plan, because some of the states actually have, they satisfy the goal, some other states don't. Okay, so that's the idea of conformant plan. And then this is basically the formal description of the progression. So here is the belief state, here are your actions, and then transition model. Remember that the transition model was defined in terms of states. If you apply an action to a state, what would be the next state? However, we need transition model at the belief state level. I don't need a new input from the user, from the domain modeler. I can actually compute for myself the transition model at the belief state level directly. Because all it's saying is the new belief state is essentially all the states S dash such that S dash belongs to the result of doing action A in state S. And S is one of the original states in the belief state. Okay? That's basically what we've been saying. It's just written down now. Okay? And then the goal test is if they basically you stop only if every state in the belief state is a goal state. Otherwise, you're not guaranteed. Because you might actually wind up ending in one of the other states. Remember that even though you think in terms of belief states, the world itself, there is no Schrodinger's cat in our worlds. In real worlds, there is no Schrodinger's cat, right? Essentially, when you do the action, you will actually reach one of the states. You just did not know where you were, and you did another action which may be non-deterministic, and yet, when you start from somewhere you don't know, and do an action which can have non-deterministic effects, people with full observability can still tell you that you are in state S79. You see what I'm saying? There is no disjunction, there is no uncertainty in the actual state that happened. Okay? It's during planning you don't know which of them you will get. And so you have to consider the possibility that you can be in any of these states, and you can only stop if all those states satisfy the goal test. Okay? And so again, you should be able to always executable actions. We described why actions must be always executable, because if not, then essentially it's both a bug and a feature. It's a feature in the sense it will be easier problem to solve, but it's a bug in the sense it's not a particularly realistic problem, because most problems don't have solutions. Okay, and then you know about this, and then we talk about it. Questions? Yes.
Does this represent probability? Or
which one?
This result.
Right now, all of this is at non-deterministic level. We are doing only non-deterministic. We are doing discussion at the non-deterministic model. Okay. What that means is only the states that are possible. That means they have non-zero probability would be in the belief state. And anything which has zero probability is not in the belief state. When you allow probabilities, notice that the number of states in the belief state makes no sense, because there are always, every state is present in the belief state. All that matters is how did you draw the probability mass such that the sum ends up being equal to 1.
So it doesn't have any significance in P.
Which one?
Result P as A.
No. Result of doing action A is stateless. Okay, that's not the probabilities. No. Okay. Now we get to finally simple observation model. Okay, the simple observation model we looked at essentially is in terms of you assume that when you are in states, in this observation model you don't need to do anything to get the observations. When you are in a particular state, that state automatically gives you a percept. Okay, now you can say I can generalize the model such that actually I have to open my eyes. It's not the case that rover suddenly knows all the percepts on Mars. It has to use the various cameras to get various percepts. But the simplest model is when you're in the state, you get a percept directly. Okay, and so there is, just as you have a set of states, you have a set of observations. So you have some set of states, S1, let's say Sn, and then there is some set of observations O1 to OM. Such that, maybe S1, S3, S7, they all give O1 as the observation. Okay? So multiple states can give a single observation. Okay? So now if you get O1, if nobody else gives O1 as the observation, if you get O1, now you know that you probably are in S1, you are in one of S1, S3 and S7. Then the question is it perfect sensing or imperfect sensing? If it is perfect sensing, in fact, if you started, so if it's perfect sensing, that means you are either in S1 or S3 or S7. Okay, if it's imperfect sensing, because what happens is the probabilities are written this way: O given S1, O given S2, O given, S3 given S7. These are all 1. If it's imperfect sensing, I might actually have, this is 0.9, this is 1, and this is 0.7. Notice that doesn't have to add up to 1, right? It's just a noisy observation. When you're in that state, you with 90% probability you'll get O. When this state, you'll 100% probability you'll get O. In this state, you get 70% probability you'll get O. Okay, if you have this, then you have information about likelihood over the states. If you have this, then you think all of them are equally likely. You don't know anything specifically about which state is more likely or less likely. All the other guys have 0 likely. Now, of course, this whole entire discussion about the probabilities is sort of moot, because if you are in the non-deterministic scenario, then the belief state you have does not have probabilities. So even if I have probabilities for the observation, what do I do with them? I don't know what my original probabilities are, so even if I know this observation, it makes no difference. If on the other hand, if I'm in stochastic case, then I will have an actual belief state which has probabilities associated with each of the states. Then I can use Bayes' rule to actually compute the posterior probability of the states given the observation. Okay, so that's basically what you do. That's basically the filtering problem. Okay. Yeah, this is basically what it is. Okay, so the probability that you have state SK, given that you just had observation OI, is probability OI given SK, which will be known from your sensor model, times probability of SK by probability of OI, which is the prior probability of OI. Now, since all the states will have the same denominator, you can basically just compute just the numerators and then make sure you multiply all of them by alpha factors such that they add up to 1. That's the normalization. So you normally just say probability of S given O is proportional to probability of O given S times probability of S. Right? And probability of O given S comes from the sensor model, probability of S comes from the previous belief state. The belief state that you think you would be in based on your simulation of the action from the previous belief state. Okay? And the other thing we discussed a lot last time is that when you have observations, then essentially what they're doing is, from a non-deterministic point of view, if you're in the non-deterministic model, at runtime, observations essentially just reduce the belief state size. Okay? Whereas at the planning time, they partition the belief state into two, or if it's just a single observation, then they partition into the states where O would have come and the states where O wouldn't have come. Okay? Okay, so we went over all these points last time. All these points we went last time, and then the one thing is, even if you have observations, you can decide not to use them during planning, in which case you are essentially doing conformant plans. That means the plans which don't do any observation actions, or they don't take observation into account. Okay. And the contingency planning basically, so those plans would be of the form do A1 followed by A7 followed by A9. So the state is telling me O, state is telling me O7, state is telling me O9. I just ignore all of that stuff. I just do what I decided to do from the beginning. Okay? And then these plans on the other hand will do A1, and then if it is O, then you do A7. If it is O, if it's O1, you do A7. If it is O2, then A5, for example. So if you take sensing into account, you will get 3 plans like this. And then you have to find the best of these 3 plans. Okay?
So cannot we convert this contingency plan into conformant plan by adding like states in middle? If A1 takes an action and it gives an observation O1 and it gives to a new state, and then we can.
So you are now basically you're talking about making the observations as state variables. That's what you're trying to say.
Yes.
That is possible. That's a strange thing to do, but that is possible. Okay, but they have conceptually very different roles to play, because the state variables are what is true in the world. Okay, the observations are what the states will give when you are in that state. Okay, and so these basically are saying that if you have observational actions, then if you have a belief state, then as you are doing actions, you get to have a better idea of your belief state. Notice this, I mean, maybe this is only a problem for me and everybody else, it's clear in their heads, but just because somebody knows where you are doesn't mean you know where you are. Do you understand what I'm saying? So when you have, so I mentioned earlier that you do a conformant plan, at the end you will reach a state where the goals are satisfied. Okay, it's an existential plan. It's like an existential proof. By the end of the plan, you would have reached the goal state. One of the goal states. Which goal state would you reach? I wouldn't know. Would you know at the time of execution? I still don't know. You know. And I've proved that I would reach one of them. So my proof is my guarantee that I would be in one of the states. You see what I'm saying? So in some sense, when you're doing conformant planning, essentially, unless you can see just from the action application, belief states shrinking and growing, which you could have seen during planning, it has nothing to do with execution. Okay, so for a planner, for an agent with no sensing, execution doesn't give it any extra information. Actually, it does give one very interesting kind of information if you get into the reward model. So just because you don't know that you are, currently on a hot stove doesn't mean the hot stove would say, oh, no, Rao doesn't know that he's on hot stove, so let's not singe him. Do you see what I'm saying? The reward of being on the hot stove would be felt by me. Okay, but then that in itself is an observation. I mean, so reward is a kind of an observation in some sense. Okay, if all you're saying, so the point is that once you have observed, when you're doing actions, then essentially during the execution, you can actually you can filter your actions, filter your belief state through the actions you have done to get the new belief states. Which, if you are getting observations, they can reduce the size of the belief state. That means they increase the certainty of where you are. Okay? And that is the state estimation problem, and that was the nice little picture I showed of things moving around. Yes?
Even if you have reward model, you need sensors to measure that reward model, right?
That's actually, it's an interesting point. So again, just as this guy was asking, can't we put observations into the state? You are saying, can't I put reward into the observation model? People have done that too, but the real question is, whether there is a reward mechanism that is independent of sensory mechanism. So just because people don't have eyes and hands and legs or whatever, does that mean that they won't be able to get reward like happiness, for example? Okay, that could be like the dopamine in your brain. For us, the dopamine in the brain. Yeah. So you shoot some dopamine, they'll feel good. Yeah. They may not be able to tell you that they're feeling good. How many of you have seen Awakenings? I already told you've seen it, right? I mean, by the way, that was the only movie I cried like a baby. I mean, if you understand any of this stuff, any of the MDPs, PAMDPs, and so on, Awakenings is actually a real story. It's a story of these people who essentially had a condition wherein it's a perfectly working brain stuck in a effectorless body. They cannot affect anything. They can't talk, they can't move, they can't do anything. And they are sensing, but how do you know they are sensing? You have no idea. Okay, and what's one of the most beautiful, I mean, the thing that happened is this guy, Oliver Sacks, who is a well-known, neuropsychologist, basically, he essentially, treated them with L-Dopa, which is like a, pouring dopamine. And for a while, they awakened from this frozen state. And then the movie itself has two of the greatest actors, Robin Williams and Robert De Niro. And it's an amazing, amazing movie. You really should see it. Okay, but the point there is these are people who actually had observations going on. You have no clue whether they had observations or not. They had sensing in that particular case. And they were able to actually feel pain and pleasure. But We don't know that. And there is nothing they could do to tell us about it. The movie itself is very interesting because they actually come out for a while. I mean, the real story itself is interesting because the L-DOPA works for a while and then they just go back to normal state, which is where it really, really, really becomes sad to me. Because in some sense, that they have a perfectly working brain. And the entire effector system has collapsed. And you don't know what that means, really. Just not having one of your fingers work and, crying like a baby is not effector system being, collapsed. None of the effectors. You can't even do, essentially, your eye movement, nothing. Everything has been cut off, okay? So, in general, coming back to your reward issue, the question is reward a different kind of internally hardwired sensor, or is it just like a sensor like, eyesight and hand movement, etc. And eyesight and touch, for example. Okay, if you think it's no different, then you just model it as an observation too. But people who you would think don't have any sensors, that means they're probably deaf, blind, and and cannot move, will still actually be able to feel pain and pleasure in some cases. So that's a difficult issue.
For example, in this problem, it's just knowing the state in which we are is the goal state, actually, because it will automatically be clean.
What?
In this case, knowing in which state we are.
I mean, so if sometimes your conformant plan guarantees that you would reach a singleton belief state, then of course, which state you are in. Sometimes it guarantees that you will reach a ternary belief state. All three states are going to be satisfying goal. In which case, you don't know which of those three you are in. And you won't know it even during execution because you don't have any sensor. Okay? And then, as I said, using sensing during search, essentially what happens is it splits the belief state into two parts. I mean, one part of the belief state where the observation will hold and the other part where the observation doesn't hold. And to ensure that you make a strong plan, you need to then progress on both this and this until they reach the goal. So eventually you will get tree-shaped plans. Okay? Which we will get in PalmDPs too. All of this is important because when you go to PalmDPs, I'm sure some of you read at least that chapter, and you realize that they basically play with the finite horizon. PalmDP essentially starts, with the last thing would be an action. And then if you have one more step, then do an action, consider possibilities of observations, and do another action. Okay? So it can, basically they search, they think over, they simulate over all possible conditional plans of depth k, if you are talking about k size horizon. Unfortunately, how many conditional plans of depth k are there? And that turns out to be a power number of observations power k. A power number of observations power k, because there are so many trees. And this is why finite horizon PalmDPs are also pretty hard. Because if you're really trying to ensure that you're getting the best plan, even finite horizon PalmDPs are very hard. Okay. Going forward, this is just basically, this is all just basically talking about how the belief state is updated using the percepts. And if you are at the runtime, you know exactly what percepts you will get. If you are in the planning time, you only know what kinds of percepts you might get. So here is the interesting thing. Suppose it turns out that my current belief state is S1, S2, S3. My model is that S1 will give O1, right? And S2 will also give O1, S3 will give O2. Okay? at the runtime, I'll only get one of these observations because I'll only be in one of the states. So if I get O1, I know I'm either in S1 or S2. If I get O2, I know I'm definitely in S3. At the planning time, on the other hand, I have to consider the possibility that at runtime I'll get O1 or O2. If I get O1 in my head, I realize that I will be in S1 or S2. If I get O2, I realize in my head that I'll be in S3. And then decide what to do in each case. So at the planning time, the observation actions are truly non-deterministic. So this is another technical point. In the space of states, you may have actions that are non-deterministic. That means if you do from S1 an action A, it might give you either S11 or S12. That non-deterministic action becomes deterministic when you go to the space of belief states. Do you understand this? In the space of belief states, all actions are deterministic because you give a belief state, you give an action, you'll get exactly one belief state. That's the definition of determinism. They are deterministic, all right, except in a much larger space called the belief state space. Right? So then, basically, you went away from non-determinism. That's why you are able to actually get line plans by searching in the space of belief states, sequential plans. Okay, but then when you introduce observation actions, that if you allow percepts, which is supposed to make your life easy, because you know more about where you are, but during search it makes your life harder. Because actually now this can either go here or here, depending on what observation you get. So it's actually non-deterministic. So observation actions are non-deterministic in belief space. Whereas non-deterministic actions are deterministic in belief space. And if you just understood this, then you really didn't sleep in this class. If you didn't understand this, you have slept at least once in this class. Okay? Because, non-deterministic at state space can become deterministic in the belief space. Okay. So how does this all generalize with uncertainty? So you can have stochastic outcomes. Basically that means you have distribution on the initial belief state. Okay, and then when you have actions with probability information thrown in, then you apply an action to a belief state, you get a new belief state, which is a new distribution. Okay, and then this new distribution is then filtered through the observations. The observations themselves might be probabilistic. And you can get multiple different belief states depending on which observation you'll actually get. But during execution itself, you'll get only one of those observations, so you'll actually get the new belief state computed. Okay, so that's what we will try to start talking about today, so that next time actually I can go more into the policies for POM-DPs. Okay, so POM-DPs are the models that you want to use when you have noisy observations and stochastic belief states. And the reward model is general. That means the general reward model. So in my little three-dimensional picture, POM-DPs are at the edge. Not at the edge actually, they're in the middle edge somewhere, because all the bad guys are in the middle. Okay. So they have general reward model, stochastic observation, noisy observations, and stochastic actions. Okay. And one thing to start from is we do know fully observable MD Markov models. In the case of fully observable Markov models, if all you're doing is predicting what happens next, then you have Markov chains. And if you have to decide, you get to control the evolution, then you have Markov relation first. That's what we discussed. And for partially observable case, for prediction, you have HMMs, hidden Markov models. Okay, and this is what we will discuss, which is decision making in the context of partial observability, which is POM-DPs. Okay, so a POM-DP looks like this. You are essentially, the world itself is going from state 0 to S1 to S2, etc. But when you are in state 0, you will get some observation Z0, there is observation Z1, there is an observation Z2. And then based on the observations, the agent does actions. Okay? If I do action A0 here, that will affect, if you do action A0 in state S0, you will get S1. In this case. Okay, in the execution, you got S1. And not only that, because you are in S1, S1 will then emit the observation corresponding to that state. Okay, based on that, you may have decided to do an action A1, and then essentially now you have a new state, depends on the previous state and the action you did. Okay, your decisions depend on the observations you are getting, and the states themselves depend on the actual previous state. Okay. Right? And then there is this whole thing about rewards here. Because as you are in the state, you will just feel the reward. This is that point about this is a very interesting question. If a state can be fully observable by giving you a unique kind of reward, right? That means you'll get pi reward, let's say. And nobody else in the world gives you pi reward, pi being this irrational, transcendental number pi. Then you know which state you are in. You see what I'm saying? And that's a very reasonable question to ask. So is your question as to can we not put the observations back, observations back into the state space. Okay. Anyway, so the assumption here is that the rewards, we still want to stick to the normal MDP model. So there is the rewards being experienced. Okay. Now the question is, if I have this model, then this is partially observable Markov decision process. Now, why is this not a Markov decision process? Well, of course, it's partially observable, right? Okay. This stuff, this basically goes towards, and the optimality criteria. So the one question is, what is the optimality criteria? Optimality criteria is find the policy that will give you the optimal expected cumulative reward. Optimal expected cumulative reward. Okay, and lots and lots of applications. Actually, let's say this. So if you have PALM DPs, and if you're trying to find the optimal policies for them, complexity-wise, for finite horizon, PALM DPs are p-space hard. Okay, and if you have no observability, then they are only NP complete, and only in an AI class would you say only NP complete, right? Because that's like a cause for celebration. Yeah. It's not at least p-space hard, right? Now, first I want you to understand how come if you don't have eyes, your decision making suddenly became easier. I hope you know now because I've repeated this ad nauseum for the last 2 classes. Sometimes decision making problem becomes easier if you don't have sensing. Your success probability goes down for sure. But at least you won't have to, tax your brain, in getting whatever success you get. For infinite horizon MDPs, PALM DPs, undecidable. Which is more like tells you, see remember PALM DPs are pretty sad problems. This is real world. And so in some sense, optimal policies, just as you don't do optimal policies for anything. And so you can tell people that what do you expect me to do? It's an undecidable problem. It's actually worse than, the life you live is worse than PALM DPs, by the way, because you can't assume that it's just you are dealing with nature which doesn't even acknowledge your existence. You're dealing with people like us who do acknowledge your existence. We are planning to get you down. Right? And in fact, there is this whole entire argument I may have mentioned earlier that evolutionarily we did not need anywhere near the size of the brain we have if all we had to deal with were tigers on the savannas of Africa. Okay? It was because even then they had to deal with the other people with brains. And then there was an arms race until the brains became huge. Okay? But anyway, so PALM DPs are undecidable in the infinite horizon case, and they are p-space hard in the finite horizon case, and they become easier if you have no observability. All these results are really, really depressing compared to even MDPs, which we already agreed were quite depressing. Okay, So why are we doing it is a different question. But okay, so POMDP is now you have a set of states, a set of actions. There's a transition function. There is a reward, SATR. That is the usual MDP part. Plus you have a finite set of observations that you can get, okay? And then there is an observation model which tells you what is the probability that you get that observation when you do that action in a particular action in a particular state. Okay, so that's the observation model. And you really want to think in this case, in the POMDP's case, by now it's not surprising that you need to think in terms of belief states. Okay, here's an interesting question. So belief states, it turns out, in belief states, okay, let me put it this way. POMDPs, if you think only in terms, what do they get? The agent only gets observations. The question is if the agent is just keeping track of observations, the state in terms of the observations, would it be a Markovian process? Remember, we've been saying MDP without giving our dues to Markov. Right? We said in the very beginning that the reason MDPs are called Markov is because of what? No, not at all. What? Dynamics are dependent only on the current state. That's what's Markovianity. First order Markovian means you're dependent only on the first state, the current state. Second order means it only depends on the current state and the previous state. Third order, current, previous, and the one before that. And if there is no finite number of such states, then it's not Markovian. Now, tell me why is POMDP not Markovian in the space of observations? If you think in terms of observations, why is it not Markovian? Yes?
Because the observation you got 2 states ago still is pretty relevant to try and decide.
Give me an example.
You know more if you know the current observation and the last observation than if you just know the current one.
Yeah, but basically this is partly, remember the whole smoothing problem I talked about? Based on the observations that you got all the way to the end, not only you know where you are at this, you would also know where you were in the beginning. Okay? And to me, the way to remember why in the space of observations you don't have Markovianity is again going back to lane change problem. Right? So, I was going along, there was this red car in the back of me, and then, I saw it, it was in the back of me, and, it was there in the back of me in the rear view mirror. And then after a while, I see that the red car is not there in the rear view mirror. Am I allowed to change lanes?
Yes.
What happened to this red car? Did the aliens just remove it? It just possibly went into my blind spot. Do you see what I'm saying? So the way you are supposed to use the rear view mirror, this is also driving lessons class now, is that you keep track of the observations from the rear view mirror. And if in the last 3, 4, 5, 6 seconds there was a red car and the red car disappeared, you don't celebrate and go into the red car's lane because you will be with the red car at that time. One with it. Right? Unless the red car went off into an exit. What you have to realize is that essentially because you have the rear view mirror is not full observability, it's partial observability. And it fails when the red car came into your blind spot. And you still live because you realize that there was a red car before, and those set of observations are important in computing my current state. Since I have no way of explaining its disappearance, it is still around somewhere. That's why POMDPs are not Markovian in the space of observations. So, however, they are Markovian. I'll come back to these again when I come back to this class. But they are Markovian in the space of belief states. Because given a belief state and an action, you get a next belief state. They're completely Markovian. Okay, in fact, given a belief state, an action, and observation, you will know exactly what is your filtered current belief state. Again, Markovian. Okay, now if you do have Markovian, the interesting thing we'll discuss next class is just as for the non-deterministic case, you had action transition functions defined in the space of states, but you could compute the belief space transition function directly given just the action transition function. Similarly, for POM-DPs, you can compute the probability that you will be in a belief state B dash given that you are in belief state B and you did an action A. That's what a transition model is supposed to be, right? That can be computed. We'll go through the formula, you probably already looked at it. It's obviously, basically using Bayes' rule, and the first you predict the state according to the action, then you use the Bayes' rule to change the distribution because you know what the observations you actually saw, and so you will be able to compute this probability. So now I know the transition function in the space of belief states, and I need the reward model in the space of belief states. For that, I assume if I'm in a belief state B of S, with that basically it's I'm in state S1 with 0.9 probability, S2 with 0.1 probability, I get $10 for being in S1 and $1 for being in S2, then 0.9 times 10 plus 0.1 times 1 is my expected reward for this belief state. That's my reward model. So I just converted, just before you leave, a POM-DP into an MDP. So why can't we use the value iteration and policy iteration? You can, but for the fact that all our value and policy iteration algorithms worked for discrete state spaces. Belief states are continuous state spaces. They are actually S-dimensional continual state space. Okay, a belief state is a point in S dimensions where S is the number of states. Right? And any point in that space is a belief state. Any point, not just discrete points, any point in that space is a belief state. Actions can take you little places. So you can actually remember now all your calculus about continuity, which you got to forget all this while. That's the thing that we didn't do because we said we will be focusing only on discrete MDPs, which was fine until you got to observations where the observations made the discrete MDP with observations becomes a POM-DP, which becomes an MDP in a different space. That space is continuous. That's why you need a separate value iteration algorithm. Once we figure out how that works, that's basically, some ideas from that can also be useful for any continuous state MDP. Okay? We'll stop here and come back.